Hello, this is AQA Chemistry Paper 1, 2018. I've done questions 1 to 7 on a previous video. Here is question 8. Titanium is going to be made and we've got to extract it in 2 stages, so they're going to be asking you general industrial questions, so look out for kilogram quantities later in the question possibly, and also you've got to change from thinking about the safety in the lab to the safety in industry. So, first of all, 8.1 suggesting one hazard associated with stage 1. Let's have a look at the whole reaction. Titanium dioxide, that's in paint. So, carbon, chlorine gas, that's toxic. And titanium tetrachloride, we don't know. And then carbon monoxide is poisonous as well. So, let's go for chlorine. And just, we're going to use the correct technical term. If it kills you, it's toxic. That's it. So anytime you come across chlorine, toxic is the word to use. Question 8.2, it says water must be kept away in stage 2. Let's have a look. So one reason for water becoming dangerous with sodium, so in the lab it would be a violent or vigorous reaction, but you could say anything to do with explosion risk or very violent reaction. Hydrogen production could lead to explosion. Explosion. Okay, and then we've got 8.3, why the reaction in stage 2 is carried out in an atmosphere of argon and not in air. So let's have a look. If you react anything with this in air, it would be the titanium, and it would probably go back to forming titanium dioxide again. So we just need to talk about having an inert atmosphere, because if we're talking about the noble gases, then we're just going to use the word inert. So argon is inert, and it prevents oxidation of sodium or titanium. Okay, so moving on to question 8.4. Titanium is a liquid at room temperature, and explain why you would not expect titanium chloride to be a liquid at room temperature. So let's just have a look at the type of compound it is. We've got titanium, that's a metal, and chloride, that's a non-metal ion. So we would expect giant ionic structure and bonding. And therefore TiCl4 would have strong electrostatic forces of attraction, which would require a lot of energy to overcome. Leading to a high melting point. So just say what is actually happening as well. So if it is a liquid, then if it is a liquid, this suggests simple covalent. Substance with weak intermolecular forces. I'll just show you the examiner's report. Let's see where I scored the marks first. So metal chlorides are usually ionic. Good. Metals are solid, or they have high melting points. They have strong electrostatic forces between the ions, or it must be a small molecule or covalent. So this was not necessary for me to add, but I think it was a good idea to give both sides of the story, because that's a good exam technique, to give both sides of the story. If then statements are important. Okay, let's have a look at what the examiner's report said about this question. There's a hazard key term as well. Okay, so it was least often the explanation of the bonding was done right, and how it leads to the actual or predicted melting point. And then just please be really careful. Some spoiled an otherwise good description of ionic bonding by also referring to strong intermolecular forces. So if it's a giant structure, there's no intermolecular forces is our watchword, but there's one exception, and that's graphite. Okay, moving on to question 8.5. Sodium atoms are oxidized to sodium ions. Why is this an oxidation reaction? Sodium atoms lose one electron each. So each lose one electron. Okay, and just to be sure, it says, the question asks why this reaction is oxidation, so the sodium atoms were losing electrons rather than a generalised answer. So if you said it lost electrons, that wouldn't be sufficient, because you could be talking about oxygen. Scary times. So make sure that that's you're not using pronouns. Just don't use pronouns at all. Always use the noun. Complete the half equation for the oxidation reaction. So there's sodium, and it's got one electron in the outer shell that we remember. So now when you have sodium plus, the one electron from the outer shell is over here, and it has a minus sign on it. So it's separate now from the ion. Okay, now we've got, unusually, there is a limiting reactant question. So these only come up very infrequently, once every 3 years. Here's one. We've got 40 kilograms, as we pointed out, so we've got to make sure that we've got lots of moles going on, and 20 kilograms, so we could end up with like hundreds or thousands of moles in our calculations, so that would be normal if you've got kilograms to have thousands of moles. Then we've got titanium tetrachloride reacting with 4 moles of sodium, so we have one of these reacts with 4 of these, and then it ends up with titanium and 4 sodium chlorides. Why is titanium chloride the limiting reactant? Okay, you must show you're working. So we're going to work out how many moles we've got and how many moles we need in order to complete the reaction. And you're only being asked about titanium chloride, so you don't have to go through the whole thing for sodium as well. We'll just do the ratio to say how much titanium chloride we've got and how much we would need, and therefore will it run out. So moles of titanium chloride. Okay, and then we're going to say moles of titanium chloride required. Okay, and then we'll find out whether that's enough or not. So the moles of titanium chloride and the moles of sodium, so we do need to find out the moles of sodium as well, so let's do that up here as well. Moles of Na. So the moles of titanium chloride, what equation are we going to use? Moles equals mass over mR. So I'm going to convert to grams. Moles of sodium, 20,000 divided by 23 equals 870 Okay then, so if I have the number of moles of sodium, then the number of moles of titanium chloride should be, let's have a look, what's the best way to do this? The number of moles of titanium chloride required equals 1/4 of those of sodium. So 211 moles is not enough. TiCl4 is a limiting reactant. Okay, so the other way to do it would be to say that the sodium is in excess, and you can see that there are multiple approaches in the mark scheme that you could use. Okay, question 8.8. We've got a percentage yield of 92.3% and the theoretical maximum was 13.5 kilograms. So the actual mass produced is going to be 92.3 over 100. So actual mass, use some words. 92.3 over 100 times 13.5 kilograms equals 12.5. With correct rounding. So we have 3 significant figures, so 3 significant figures is what we should quote in the answer. Question 9. Dilute hydrochloric acid is a strong acid. Why an acid can be described as both strong and dilute? So strong is fully dissociated. In aqueous solution. Now, can you see in this mark scheme it says that in aqueous solution is in brackets, so you don't have to say it, but in the 2022 paper you do have to say that. So in solution, or in aqueous solution even better, was required on the 2022 mark scheme. And dilute, it says ignore low concentration, so you have to say small number of acid particles per unit volume. Okay, so question 9.2. We have 1 times 10 to the minus 3 mole per decimeter cubed is pH 3. What is pH what is the pH of 1 times 10 to the minus 5? And so what we're looking at here is we've got to see that it's more diluted. So that means that the pH will go up. So that's 5.0. And we've got a titration calculation. So here are some results. It looks like we can see 1, 2, 3, 4, 5. How many of them are concordant with each other? So that these don't look concordant. These are concordant. There we go. So we're going to use these to calculate our mean. And it does actually tell you what concordant means, because sometimes we say 0.20 or something like that. So within 0.10, that's fine. And so we've got a concentration here, and a volume, and some more volumes. So the equation that we need is going to be N equals C times V, and V is going to be in decimeter cubed. So we've got some conversion to do. So for this one, the volume is 0.025 decimeter cubed. And then our mean volume is going to be 22.13. And therefore that is 0.02213. Wait a minute, I've missed out a decimal place up here. There you go, 0.250. And this one is going to be like this. Okay, have we got everything set up now? So we're going to go moles of one substance, concentration is our target. Okay, so we can use table method or sentences method. So I'll do sentences method first. So moles of NaOH equals concentration times volume. Okay, 2 moles of NaOH react with 1 mole of H2SO4. So moles of H2SO4 equals 0.00161162. So concentration of H2SO4 equals moles divided by volume. Okay, there's our calculation done, and let's just do the table method as well. So we've got N, C, and V. So we've got 2 NaOH plus H2SO4. So we calculate our moles first of this one, 0.002324. Then we're going to do our moles of this one is divided by 2. And finally we can calculate our concentration without putting any typos in so that we don't miss marks. That's it. There's our target. Write it on the answer line. Great. So it says that you must show you're working for this one, but you can have error carried forward for this one. Question 9.4. Why the student should use a pipette to measure the dilute sulfuric acid and a burette to measure the sodium hydroxide solution. So I've given you this question in class before, I believe, and what we're just trying to do is just to make sure that we know that we've got variable volume versus set volume. So H2SO4 requires one fixed volume, whereas NaOH requires variable volumes. But both give high precision. So rather than a measuring cylinder or something like that. Okay, and finally our mass of sodium hydroxide. So this is just a conversion of our mass to moles to mass, so we can find out the number of moles and then change it to mass. So moles present equals C times V. You don't have to put that in. 0.105 times 0.030, because we've got to convert that to decimeter cubed. Mass equals 40 times 0.315. So it's not a very difficult calculation, provided you've got both of the equations that you need in your head. So the mass here, we've got mR times moles. Okay, so 2 equations in 1 question, all for 2 marks. And that's the end of the paper. See you for paper 2.